So hello everybody. Today we are going to attempt another problem in Atiyah and Macdonald's book. So today we are going to attempt exercise 4 in chapter 2. So let me write it as chapter 3. Sorry, it's 3.4. I think the page number is 44 of the new version. So it says that we have a homomorphism of rings. Be a homomorphism of rings, and we have a multiplicatively closed set, which means that it contains 1 and is closed under multiplication. This is a multiplicatively closed subset of A. And now we take the image of S, and we have to show that S inverse B is isomorphic to S inverse T inverse B as S inverse A modules. Okay, so first of all, we need to check if T is multiplicatively closed, but which is kind of easy because because the image of 1 is 1, and if you have 2 elements in the image, then their product is also in the image. So T is multiplicatively closed. So this is where the solution starts. T is clearly multiplicatively closed. Okay, so how is so first of all we have to make sense of how S inverse B and T inverse B are a module. Okay, so we could know that S inverse B is a B module. Yes, because of restriction of scalars, because we have a map which is not exactly an inclusion map, but we have a map from S to S inverse of B, which takes an element B and sends it to B over 1. So because of this, S inverse B, we know it is a B module. It's actually S inverse B and B bimodule. But how is it an A module? Because we also have a map F, due to which we can restrict our scalars to A. So most of the times not most of the time, but sometimes half of the job is actually trying to understand the problem. So it's due to this restriction of scalars, S inverse B is an A module. So A times, let's say, B over S hold on. Yeah. No. No, so there is a little more complexity here because S is S is not a subset of B, so how can we make sense of S inverse of B? Oh, okay. So the way you can make sense of S inverse of B as the S inverse A bimodule, S inverse A module, is you think of B is an A module. Okay, so B is an A module, and so think of B is a module. It is an A module, and so S inverse B makes sense. In the setting of module, so here we are not taking this ring of fractions, but it's actually a module of fractions. And then B, how to make, so this is okay. S inverse B is a S inverse A module because B is an A module. But how should we make sense of T inverse B as A inverse A module? So B is a B module. So this means that S inverse, this means that T inverse B is a T inverse B module. But F going from A to B gives us a map but I think we can give T inverse B and S inverse A module like this. We take an element from here and multiply it by p over something like f of let's say f of t, and it can define this as ap or f of as f of t maybe. I was thinking of making this as an M into an S inverse A module by some kind of restriction of scalars, but that doesn't seem to work here, I think, and we have to explicitly define the scalar multiplication here like this, and we also have to check if this thing is let me write this as p over, let's say, t maybe. Alright, this is f of s times t. We have to check whether this thing is well defined. Maybe we can define a map from T inverse A to S inverse A to S inverse B, and then we can make a restriction of scalars. Define a map like this. Homomorphism by taking A over S and sending it to f of A over f of S. And is this thing well defined? Yeah. So this thing is a homomorphism. This is a ring homomorphism, and now we can think of T inverse B as an S inverse A module. Okay, so it took us how much? Almost 14 minutes to make sense of these two modules, and now we're going to show that these are isomorphic. Can we define an explicit isomorphism? Let's say S inverse B to T inverse B, like taking B over S and sending it to something like B over f of S. Isn't this an isomorphism as S inverse A modules? Let's see. So first of all, is this thing well defined? B of S is equals to P in I want to solve this problem in under 30 minutes, and it's already 15 minutes. For some u belonging to because the action of A on B is applying F on the scalar and then multiplying with the corresponding element in B. And now this thing belongs to T, and Okay, so this thing is well defined. And now we have to check is this thing is an is it additive? But I think that should be easy. Let's see. So this thing should go to f of s prime b plus f of s b prime over f of s s prime, which is this thing is the same as everything is additive. The last thing we have to, and why is this thing surjection? Because every element of T inverse B, every element in T inverse B is of the form B over f of s for some s belongs to s. So this thing is clearly surjection. And why is this thing is injection? Because if B over f of s is equals to 0, then B times something this means that B times something it means that B times something in T is 0, which means B times U, f of U times B is equal to 0 for some U belongs to S. And now what this means that U times B is equals to 0 in B as a module and U belongs to S. So this means that B over S is equals to 0. Because B element of B acted by some element in S is 0. So B over S is equals to 0. So it's injective. Thus, let's call that phi. Phi is injective. Finally, we just have to show that it's nice under scalar multiplication, and I think it should be easy too. So phi, here we have S inverse B and then T inverse B, and T inverse B, this is T inverse B module, and then we restrict scalars to S inverse A. Okay, so B S inverse B is an S inverse A module because B is an A module. So if we multiply it by A over S times, let's say, B over something like T, then we get A times B over ST, but A times B means this is f of A, B over ST, and then by definition of phi we have this thing, and then this thing is then A over S dot B over F of T, because the scalar multiplication is defined here. It's actually a restriction of scalars which is defined this way. This thing is already a T inverse B module, and we restrict the scalars to S inverse A, and this restriction is defined this way, and it's well defined. We already checked, and it's also it is a ring homomorphism. So we have this and A inverse S, so it means this times F of B over T, and we are done. So thank you, and we are going to stop.